So now I want to introduce our speaker. So Dr. Natalie Batalha has been a professor of astronomy and astrophysics at UC Santa Cruz since 2018. Before that, she served as the scientific lead for NASA's Kepler mission. It was really a fundamental mission that transformed astronomy in the way that we think of it, because it helped us discover over 2,700 exoplanets and another 2,000 candidate planets that we're like pretty sure are planets, but we need a few more data points to convince ourselves for sure. In 2017, this led to her being listed as one of Time's 100 most influential people of the year. In particular, she's identified planets that might be able to sustain life, which is one of really the biggest questions we can ask about ourselves, right? Are we alone? Are there other living things out there? And she also led the analysis that led to the discovery in 2011 of the first confirmed rocky planet, so planets like the Earth and Venus and things like that, outside of the solar system. So for the first time ever, we were sure that a rocky planet existed somewhere else in the universe. And her research continues to focus on exploring the diversity of planets that she's helped us find, as well as continuing to search for life. So please join me in welcoming Dr. Batalha.
Thanks, Lauren. Can you guys hear in the back? You can hear okay? All right. Welcome. Lauren used this word exoplanet. Exoplanet is orbiting another galaxy, so out of the system. So we're searching for where life get a toehold, places that are reminiscent of Earth. And we're trying to understand our own, the sustainability of Earth. There's this weird beating, and I don't know what it is. Is it bothersome?
No, it's not.
It's not? Okay, maybe it's only in my head. You're in a very special place. Lick Observatory is a very special place. It's been a premier research institute, and it takes center stage in my life, going all the way back to my undergrad. When I was an undergrad at Berkeley, I used the telescopes here, and as a graduate student at Santa Cruz, I used the telescopes here. And as a postdoctoral researcher, we rented a dome, or actually they gave us the use of a dome when I was at NASA, to build a robotic observatory concept that would turn this Kepler mission. So I've been using the facilities here at Lick career for various reasons. So my observing exoplanets with Webb Space Telescope. So I'm going to be focusing on we've been since the launch of this Webb Space Telescope. It was Christmas of 20. It June, July. We've been slogging. So, exoplanet discovery. How do we even orbit other stars? There's this misconception united the planet, not planets. Part is that stars are really house, and planets that orbit them are very, very like the ratio of those brightness is something to 1 for a planet. So not only are we overwhelmed, but also we have planets are so distant. So that means we have to that infers. I think I'm going to take my earrings off.
It seemed like it's more clear when you have it closer to your mouth. But
I think it might be my earrings. Hold on. Sorry. It wasn't doing this for the last talk, so I don't know what's going on. Let's see if that improves it. All right, so we observed something about the star that tells us that there is a planet orbiting it. These are called indirect techniques, and there are a few of them, but I'm going to focus on one technique in particular that's called the transit method. It's eclipsing. This is an eclipse geometry. And so when we observe this system through our telescope, we don't see a disk that is the star and a tiny dot that is the planet. All we see is a blur of light, but we can measure the brightness of that system, and we can measure it or monitor it over time. And when a planet eclipses in front of its star, it's going to cause a dimming of light. And that dimming of light will repeat. So we say that the planet is transiting across the face of the star, and that's why it's called the transit method. So in the 1990s, there was this idea that we had new technology, detectors, kind of like what you have in your cell phones, that were capable of detecting brightness or measuring brightness to a precision of about 1 part per million. Okay, so that's like seeing the San Francisco skyline and noticing that one person in one window lowered the blinds by a couple centimeters. Okay, that's the precision that you need to see this kind of dimming of light to and from an Earth-sized planet. But detector technology was that good. And so this individual, Bill Barucki at NASA Ames, started proposing this technique to do it in space, because you couldn't reach that precision if you were going to observe through the Earth's atmosphere. So that mission was proposed 5 times. First time in 1992, and it was rejected, 94 rejected, 96 rejected, 98 rejected, and it was finally selected in 2000, and then we flew the mission in 2009. So between 2000 and 2006, we did the robotic observatory here at Lick Observatory, and then learned how to process the data in time for launch in 2009. So I want to just give you, right at the beginning of this talk, a big picture view of what this Kepler mission accomplished. And I'm going to do that through a technical plot. It's a scatter plot. And I'm measuring on the y-axis the planet radius, because this technique tells you what the radius is. How big the disk is that's eclipsing the star tells how, or results in a dimming of light of a certain size. So by looking at the dimming of light, you get the radius of the planet. And then you get the orbital period, because these dimmings of light happen periodically. And so every dot on this plot is a planet that was known before 2009. The first one was discovered in 1995, announced at a conference in Florence, Italy, that I just so happened to be at. I was a third-year graduate student at the time. So I feel like I've had a front row to exoplanet discovery since the beginning. What you notice from this plot is that all of these points, something like 90%, are larger than Neptune. Right? So what we were detecting from the ground were predominantly giant planets, or those planets that are equivalent to the giants in our solar system. So from 2009 to 2013, Kepler stared without blinking at one patch of sky and found transiting planets and added these yellow points to the diagram. About 5,000, actually, points were added to this diagram. As Lauren said, about 2,800 or so are confirmed through other techniques. Of the other 2,000, 90% of them are bona fide planets. Statistically, we know that. Now, patterns emerge in this diagram. We have a statistical sample. I can now study exoplanet demographics. I can use this data and learn various things about the diversity of planets and how common they are in the galaxy. So let me just tell you some of the highlights. First of all, the diversity of planets in the galaxy far exceeds the diversity of planets in our own solar system. There are lava worlds. There are ocean worlds. There are planets orbiting 2 stars, not 1. There are planets orbiting the oldest stars in our galaxy, 12 billion years old. There are baby planets. There are planets orbiting dead stars. All kinds of planets are out there. And what I can do from this sample is this is what we observe, but there are a lot of observational biases. For example, the fact that this part in the bottom right is devoid of planets doesn't mean that they don't exist. It means that I'm not sensitive. Our instruments are not sensitive to them. So those are observational biases. And in order to understand how many planets are in the galaxy, I have to correct for all of those biases. But that's what we built this thing to do. So we know how to do that. And when we make that correction, we learn that we can actually compute the average number of planets per star. And so what we learned from that is that every star in the galaxy has at least one planet. And I'm saying at least because Kepler was sensitive to planets orbiting inside of an Earth orbit and larger than an Earth radius. We haven't even started to tap into the Mars-sized planets or the Jovians out at long orbital periods. Okay, so that's, I don't know how that switched, sorry. So when you look up at the sky tonight and you see a pinpoint of light, think of it not just as a star, but as a whole planetary system, because it is. And after studying this and doing these calculations for years and years, I really had that internalization in a very visceral way, just outside jogging at night one night and looking up at the sky. And in that microsecond, I saw the pinpoints of lights as planetary systems without thinking about it. So it's an example of how science really changes fundamentally how we perceive our universe and our place within it. Now, people are very interested to know how many of, I don't know why that's up there. I did not write those words up there. I must have been my call. I gave a public lecture with a colleague a few weeks ago in San Francisco. He must have written that. But I will explain to you what the habitable zone is. So the big question is, which of these planets are potentially inhabitable? Okay? That's a huge question because we don't know if complexity arises in the universe in the same way everywhere. There are reasons to think that it might. Besides hydrogen and helium, the most common elements in the universe are carbon, nitrogen, and oxygen. What are the most common elements that make life? Hydrogen, carbon, nitrogen, and oxygen. So that's probably not a coincidence. Life on Earth is quite diverse. There's lots of properties of life. We encode genetic information through DNA. Does all life do that everywhere? We don't know. There's all kinds of questions like that. But no matter how diverse life is on planet Earth, the one thing that all of those life forms need to survive is liquid water. They might not all need oxygen. They might not all need or eat the same things. I mean, there's all different kinds of organisms, but they do all require liquid water. A solvent. You need a solvent in chemistry to break molecules apart and build new things, right? To make a metabolism function, you need a liquid, you need a solvent, right? And there's actually, surprisingly, a limited number of solvents that'll do what we want it to do for life, to enable life, at least at the temperatures where chemical reactions would be productive. So anyway, on Earth at least it's water. So then we just say, okay, fine, we're going to take that as our first initial guess and say that life requires water, so let's go searching for the water. And then we say, all right, well, if you're orbiting too close to your star, water's probably going to all boil away eventually. If you're too far away, it's going to be locked up in ice. So there's a sweet spot in between that we call the habitable zone, and that's colored or shaded green in these three cartoons. And there are three cartoons because stars have different luminosities and temperatures. A really hot, blazing star, you're going to have to back up further away to be in that sweet spot. A very tiny, dim campfire, you're going to have to cozy up next to it. So the habitable zones are at different distances. All right, that's fine. So Kepler measured the radius and the orbital period, but Johannes Kepler himself taught us in the 1600s that there is a relationship between orbital period and distance. So as long as I know how bright my star is, I know if a planet is in the habitable zone or not. All right, so then I ask myself, all right, of these 5,000 planets, how many are orbiting in the habitable zone and are roughly Earth-sized? And I call that eta Earth, that statistic. Eta is a Greek letter, eta sub Earth, which you don't need to know. Now, I want to tell you and share with you what that result is. What does it teach us when I do that calculation? And so the first way I'm going to share that information is to have you imagine the Milky Way galaxy. This is an artist rendering of it, and now we're going to shrink it down to the size of the continental United States. Okay? And there we are, in the San Francisco Bay Area near the shores of the Pacific, and we're going to stand here at Lick Observatory. Well, the Pacific is over there. We're going to look out across the continent and say, on this scale model, where would the nearest potentially habitable planet be? Okay? And the answer, it turns out, is right over here at the 3-meter telescope on the other peak. Like really very close, within 10 light years, which is a tiny distance on galactic scales, the galaxy being about 100,000 light years across. All right, so potentially habitable planets are actually really common. And if I take that statistic and I scale it to the size of the galaxy, or I say, all right, how does that translate to the average number of potentially habitable planets per star? It turns out that that's about 50%, 25 to 50%, depending on how you calculate it. And so that means that in our galaxy alone, there must be at least something like 20 billion potentially habitable planets. And the nearest one is pretty close. Not only is it pretty close, we know how to build the technology to actually observe it and see if it's a living world. So that singular fact, which happened, I think it was first published around, 2015, kicked off a series of things that happened. The government became very interested in this. Congress actually added an objective to NASA as a space agency. Objective number 10 is to study the origin, evolution, and distribution of life in the universe. So now that's one of NASA's top 10 mandated goals. All right. And now the astrophysics community, through the National Academy of Sciences, recently put forward a recommendation to the government that the next big flagship mission that NASA builds should be the Habitable Worlds Observatory to find biosignatures or to find evidence of living worlds. So that is going to happen probably within the next 20 years. Such a mission will launch. Okay? All right, so that's all I'm going to say about exoplanet discovery. What I want to do now is shift gears a little bit to the James Webb Space Telescope, which is what I've been doing most recently. This is NASA's last flagship mission. It's a 6.2 meter telescope in space. So let's talk a little bit about telescopes. This is how it started. This is 1610. This is a replica of Galileo's telescope. He was the first one to use a lens with magnification, about 20 times magnification, and pointed it at the cosmos and recorded many observations that were really just groundbreaking. He observed the phases of the planet Venus. He observed craters on the moon. He observed the large Jovian satellites, the four largest satellites of Jupiter, showing that other objects orbit around larger objects. So simultaneously, we were shifting from the geocentric to the heliocentric model of the universe. So these were really critical observations. All right, so this lens that's inside this telescope, which is about 2 feet long, is 1.5 inches. So tiny. I don't even think you can buy a 1.5 inch telescope at Target. I don't think they would make that. And the legend is that even Galileo's friends actually had trouble making out objects in this telescope because it was difficult to see. It didn't have this clear vision that you're going to have when you go over to the 1 meter telescope, nickel telescope over here. All right, so that's how it started. Now fast forward just 400 years. That's not that much, right? And now we are building telescopes like the James Webb Space Telescope. Here is an artist rendering of it. As I said, the James Webb Space Telescope is a 6.2 meter telescope, so that's about 250 inches across compared to 1.5. And it is a telescope that was built you're familiar with Hubble. The Hubble Space Telescope took beautiful images, and its images are just fabulous. The Eagle Nebula, I mean, so many iconic images. The James Webb Space Telescope also takes really beautiful images, but its power is in observing spectra, doing spectroscopy, and I'll talk a little bit about that in a second. All right, but let me pause and say a little bit more about what telescopes are for. Telescopes are light buckets. So here's an analogy with rain buckets. The purpose is to collect light. And the more light you collect, the more sensitivity you have to see faint objects. So bigger the telescope, the better. So for example, Galileo's 1.5-inch telescope compared to Webb's 256-inch telescope, Webb is going to collect 30,000 times more photons than Galileo's telescope, all right? That means you're going to be able to see much, much farther. I mean, it's literally, Galileo's is a thimble of water compared to a swimming pool, okay? All right. So that means that we can see further back, we can see more distant objects, we can see faint objects at the edge of the universe. So here's a cartoon showing different telescopes and how far they can see because they just collect more light. And because light takes a finite amount of time to arrive from its source to our telescope, we're essentially seeing back in time when we look at these objects that are at the edge of the visible universe. And the James Webb Space Telescope is looking back to the first 200 million years of the formation of our universe, seeing some of the very first stars that became visible and luminous. Now, a lot of astronomers are observing the very most distant things and studying images like this one, which you might have seen. This was the early release observation that was published in July of 2022 when the James Webb Space Telescope first opens its eyes to the universe. And so what you're looking at, imagine you're in a meadow and you walk up to the edge of a forest. And there's lots of trees in this forest, and you look into this forest, and maybe there's a chink in the forest where you can see to the other side. You can see maybe across the forest to the other side where it's luminous, through this little chink in the forest. That's kind of like us embedded in our galaxy. We're embedded in all of these stars, but there are chinks where we can see out beyond our galaxy. And this is one such chink in our galaxy. You're looking at a very small space, maybe smaller than George Washington's eye on a quarter held at arm's length, a grain of sand. And in that tiny chink, if you look closely enough, you can see literally thousands of other galaxies on the other side of the forest, outside of our galaxy. So the James Webb Space Telescope is really good at this, at doing this kind of thing. But I'm here talking about exoplanets. Why? They're very close, but they're very faint. So this kind of a telescope is going to be great for observing the faintest things. And planets are these little crumbs that are very faint. Okay, larger telescopes also yield higher resolution. If you've got a bigger eye, you can see more detail. And so here I have an example of galaxies, simulations of galaxies taken with a telescope like Hubble versus a telescope like the James Webb Space Telescope on the right. And so you see that amazing detail just by way of having a bigger telescope. And of course, if you put a telescope into space, the motion and different layers of the atmosphere at different temperatures and how they flow, all of that creates the twinkling of the stars. It actually takes a beam of light from a star and refracts it in different directions, so that by time it reaches your telescope and you take an image of a star, it's actually going to look something like this on your detector, and it should be playing. And with time, it's actually going to move around and blur. Now, we have a lot of technology. Some of you heard about the technology here at Lick Observatory to correct for that, but it is a lot harder when you're observing on the ground. You have to apply certain technology to it. Having a telescope in space makes that much simpler. So you avoid the blurring effects of the Earth's atmosphere, but also even changes in brightness. All of this moving around causes the brightness to fluctuate just from the atmosphere. Okay. So here's an example. This was also an early release observation from the James Webb Space Telescope of Stephan's quintet. These are interacting galaxies with just full of amazing structure that we can study. Fun fact: how many of you have ever seen It's a Wonderful Life, the Christmas movie? Yeah, George Bailey, right? So that movie opens up with the angels talking to each other, and they're represented by galaxies. That galaxy is Stephan's quintet. The angels are Stephan's quintet. And next time you'll see it, you'll laugh because the images are so blurry and terrible compared to what we have with the James Webb Space Telescope. All right. Because we can see such detail, besides observing these distant galaxies, we can observe faint nearby things like planets, but also like the protoplanetary disks. This is the material, the debris that is circling the star that's left over from its formation, from a giant molecular cloud. And planets form out of that debris. And so we'll be able to see molecules inside of those disks. All right. Now, I said I wanted to talk about spectroscopy. I mean, really what we're doing with telescopes is we're extending human senses. We're making them more powerful, right? We're making our eyes go out into the universe in a very, very dramatic way. And so it's like having a superpower, right? Another way that we get a superpower by building these instruments and using these telescopes is that we get to observe parts of the electromagnetic spectrum that we can't see with our naked eye. So Superman, for example, had X-ray vision, right? Well, what is this electromagnetic spectrum? Newton played around with prisms in the 1700s, and he took sunlight, put it through a prism, and saw that it got separated out into a rainbow. Right? Its colors got separated out. That's a spectrum. And if we measure the amount of light that's coming at every color, we get a lot more information about the universe. It's extremely powerful. Now, our eyes are only sensitive to the optical, which is this tiny little part in the middle. There's all of this other radiation that our eyes are not sensitive to. So if we can build instruments that are sensitive to those wavelengths, it opens up a whole new window of information for us to learn about the universe. Okay? All right. So the James Webb Space Telescope operates in a part of the electromagnetic spectrum that is called the infrared. It's labeled IR. This is lower energy. It's often used to look at like heat. I mean, we are radiating. Every human in here, sitting in here right now, is radiating infrared radiation just because you have a temperature. You're 98.6 degrees. If I had infrared goggles, I would see you radiating, okay? Now this image is an image in the optical. So you see the meerkat, you see the freshwater crocodile there, you see their surface colors, pigments, and all of that. If you were to look at this in the infrared, though, you would see something completely different. This is what they might look in the infrared with some false color imaging. So what you notice is that the meerkats are literally glowing. This is what I would see you as if I had infrared goggles right now, because you have meerkats, like us, are warm-blooded creatures, right? Now, the crocodile is not as bright, right? But he's brighter than the thing he's lying next to on his right. Maybe he's about as bright as this little patch in the lower left-hand corner here. And so just by looking at this image in the infrared, I can learn that the crocodile, being a cold-blooded animal, has about the temperature of the warm water that he was swimming in before he crawled out onto the bank, and he still retains that heat. So you learn different things when you look at different wavelengths. And what Webb can do in the infrared, which is very powerful, is it can actually penetrate, like Superman seeing our bones through with his X-ray vision. The James Webb Space Telescope with its infrared vision can see inside of the dust clouds where stars are forming. And that gives us a lot of information. So for example, here on the left is the Eagle Nebula, or the Pillars of Creation that the Hubble Space Telescope observed. And those clouds look very opaque. And what you don't realize is that deep inside those clouds, literally hundreds of stellar nurseries are forming newborn stars and new planets today. And so in the infrared, if you look in different wavelengths, you can see inside the dust. It's like having Superman's X-ray vision, but in the infrared. Okay, so if I were to take the sunlight and put it through a prism and separate it out into a rainbow, I'm often, when I give media interviews, I've been forbidden to use the word spectrum by very reputable media sources like 60 Minutes. They would not allow me to say the word spectrum. I had to say only rainbow. So yes. So yes, this is a rainbow, but I'm gonna call it now a spectrum. And I'm gonna try really hard not to say rainbow, even though that's been ingrained in me. All right, so if I take a spectrum of the sun at very high resolution, I see that the brightness of all these colors, it's luminous at all these colors, red, orange, yellow, green, blue. But if I look carefully, there are some places where there's missing color, where it's dark, less energy, okay? And we call those absorption lines. Let me use the forest analogy again. Let's say, I'm standing in front of a forest or just a group of trees. I have a group of trees like this at my home, some oak trees. And our dog loves to play catch. And so we throw the ball absolutely as far as we can just to get the dog off occupied for a while. But I have to throw it through these trees. And most of the time it kind of makes it through the trees because there's lots of open spaces. But sometimes it hits a branch and doesn't go anywhere. So that's kind of what's happening here. Sunlight, or photons, are streaming out of the nuclear furnaces that are inside the core of the sun. But then it hits the atmosphere, and some of those photons knock into atoms. And those atoms stop them, absorb them, take them out of our line of sight. And so each atom in the solar atmosphere will gobble up very specific wavelengths of light, very specific colors. Wavelength is a measure of color. So hydrogen, for example, it has a type of photon in the red color that it loves. It has another one in the blue, but sodium has one in the yellow, right? So every atom has like its own chemical fingerprint of patterns of these missing colors that it produces. So if I observe this, I can recognize those patterns, and that tells me what the thing is made out of. And we apply this technique to stars, to planets, to galaxies, to supernovae, to star-forming regions, everything. And it's not just elements, it's also molecules that do this. Water molecules, methane molecules, sulfur dioxide, all of these molecules have their own unique pattern. And this is why the James Webb Space Telescope is so powerful, because every single instrument on board has a spectrometer that creates a spectrum. All right? Now, here is a compendium of solar system objects. And superimposed on every solar system object is a squiggly line. That's a plot of the amount of energy that's being reflected off that planet as a function of wavelength. And so where that line dips down all of a sudden corresponds to an absorption line. Okay, so it's a graphical representation of not a rainbow, a spectrum, right? So this is what I want to do with my exoplanets. I want to use the James Webb Space Telescope to look at these absorption lines so that I can figure out what the planets are made out of. When I do this, I transcend what we could do with Kepler, just measuring orbital period and radius. And these exoplanets, these objects that we identify, they start to become bona fide worlds because they start to take on a personality. I know if they have greenhouse gases. I know if they have an atmosphere or not. I know what that atmosphere is made out of. I know if that atmosphere is primordial or was outgassed later. It gives me all kinds of information, and these worlds start to become more like destinations. So to use the James Webb Space Telescope in this way, I'm going to actually use transiting planets again. We're going to go back to these transiting planets because when a planet is in front of its star, some of the photons from the star are going to go through the atmosphere of the planet. You can just barely see it. See this kind of orange haze around the limb of the planet projected against the darkness? That's the planet's atmosphere. And so as that planet moves onto the stellar disk, those photons are going to, some of them are going to go through the planet's atmosphere. So all I have to do is collect all the light when that's happening, and I have to tease out which photons are coming through the atmosphere of the planet and which aren't. Right? Okay, so you saw a cartoon like this before. This is a cartoon of a planet transiting in front of its star, and then you see the brightness measurements, and when the planet eclipses, the brightness dims. Okay, Kepler did that. The difference with the James Webb Space Telescope is it measures, wow, change slides for me. It measures that dimming of light in thousands of colors simultaneously. Okay? So that means that, and so here's a stack of those, an example. All of these are transits, but taken at different colors. So if I reach a color that I know, let's say carbon dioxide loves, then the dimming of light should all of a sudden get a little deeper, because more of the photons are going to be taken out of my line of sight by the carbon dioxide molecules. And that's exactly what happens. So we did this for a planet called WASP-39b. WASP-39b is a Jupiter-sized planet orbiting about 10 times closer to its star than Mercury is to our own sun. We call these types of planets hot Jupiters. And I don't know if you were watching Colbert. How many of you watched Stephen Colbert? Okay, a lot of you. Last week, he reported news about exoplanets, and one of them was a hot Jupiter. So he tried to make a joke about a hot Jupiter. I don't know if it was very funny. It was moderately funny. He showed this artist rendering of a hot Jupiter, and he said, yeah, this is referred to a hot Jupiter. Now it's really not going to be funny when I say it. And he said, which sounds like something a cowboy would say when he stubs his toe. Hot Jupiter, that's smart. Okay, some of you are laughing. I didn't think it was that funny. All right, so yes, WASP-39 is one of these hot Jupiters, and so here's an example of the data. And so there's the dimming of light, but I colored the points red, blue, and green to show 3 different colors. And so you can see down here in the blow-up that at the green color, or the wavelength corresponding to the green points, the planet eclipsed a slightly more light. I don't know why the computer keeps doing that. It's strange, than it did at the red. And so these green points are at a color that corresponds to carbon dioxide. And so I can calculate for each color how much light is being blocked by the planet. And I get a squiggly line like this. And all these bumps and wiggles are due to different molecules. So I've got water molecules, I've got carbon monoxide, carbon dioxide, this really interesting sulfur dioxide line, and all of these lines tell me something about the nature of this planet. In fact, the sulfur dioxide is particularly interesting because it only exists in the atmosphere because starlight is breaking apart water molecules and causing a cascade of chemical reactions that create sulfur dioxide. So now we get an idea of the chemistry of what's actually happening in real time in the atmosphere. Another very interesting planet that I want to call your attention to is called K218b. And it's colored in this artist's impression as a blue sphere, kind of like a Neptune. I don't know if they're actually blue, but I'd like to learn. But there's something very interesting about this planet. It's about 2.3 times the size of Earth. So here's a histogram, or a bar graph, of all the sizes of the planets that we know about so far, okay? I colored these over here brown because they're kind of sizes that correspond to a rocky planet. And over here I colored them blue because they're more or less the sizes of the giant planets. But what's remarkable is that the most common type of planet that we know about so far is this gray area in between. And up there I put the sizes of the solar system planets, and you can see in our own solar system we don't have anything that size. And yet they're the most common in the galaxy. What are they? We don't even know what to call them. Sometimes we call them super Earths. Sometimes we call them mini Neptunes. We don't know. And I'm very curious to know if those are potentially habitable planets. And so that's what K218b is. We want to know if it's more like a super Earth or more like a mini Neptune. So we set out to observe it with the James Webb Space Telescope using the technique I've already described to you, and we get the same kind of bumps and wiggles. And from this bumps and wiggles that show how much light the planet is blocking at each of these different colors, we know that the planet has a lot of methane, for example. Not carbon dioxide like the giant planet had, but also very different than a Venus, for example. And so we combine all of this information, the fact that it has dimethyl sulfide, that it has a small quantity of carbon dioxide and lots of methane. We can combine all of that information and we can start to piece together if it's more like a super Earth or more like a mini Neptune. And it's literally someplace in between. All right. The other interesting thing about K218b is that it orbits in the habitable zone of its star. So that makes it also even more compelling. So our theoreticians go away and they look at this information and they try to ascertain what the interior structure of this planet might be. And so there's a lot of complicated layering and different compositions here. But the point that I want to drive home is that from what we can tell, K218b is something like this lower left diagram that we're calling Haitian planets. It looks like it has a liquid water envelope over a rocky core with a very thin layer of hydrogen. So it's similar to a scaled down Neptune, which would actually be more like the upper right-hand side, perhaps. No, a mini Neptune, it would be this one. Kind of similar, except its hydrogen layer is a lot thinner. And the reason that that's really important is because our theoreticians tell us that life could potentially exist in the liquid water underlayer. And those theoreticians are putting forward and proposing maybe some biosignatures, some metabolic byproducts that such life might produce. So that's very exciting. All right, let's see. What else do I want to share with you? One more factoid. You might have heard about a planetary system called TRAPPIST-1. This is a planetary system whose host star is not a star like our own sun at all. It's not a G-type yellow star that's pretty luminous. This is a red dwarf. It's very tiny, about 10 times smaller than the sun. It's very cool. And if you want to be a habitable planet, you got to cozy up next to this thing. But it just so happens that this planetary system has 7 more or less Earth-sized planets orbiting in the Goldilocks zone of the central star, TRAPPIST-1, and that whole entire planetary system would fit inside that small circle in the diagram of our own solar system. That's how scaled down it is, okay? This is a very interesting system. It's only something like, I think, 40 light years away. It's pretty close. And so this is something that we'll be studying carefully with the James Webb Space Telescope. So far, what we have done is observed the innermost planets, B and C, and maybe D, I think, has some observations, to test simply, does the planet have an atmosphere or not? And the way we do this is by looking at the thermal radiation, the heat coming off of this planet. You can imagine a planet like Mercury, let's say. Mercury doesn't have an atmosphere, and it's orbiting super close to its star. The day side temperatures on Mercury are something like 800 degrees Fahrenheit, something incredibly hot. The night side temperatures on Mercury are like minus 200. I mean, it's incredibly cold, right? Now, you wouldn't have that big difference if Mercury had an atmosphere, because atmospheres redistribute heat, right? Climate, think climate. They keep the day and the night side relatively the same. Earth, I mean, today it was what, 84 degrees? If you look at the weather for Lick Observatory tonight, it'll drop down to like 64, maybe 20 degrees different between day and night, right? But if you don't have an atmosphere, that is a very dramatic difference. So what astronomers are doing is comparing the day and night side temperatures on these planets by looking at the thermal emission from these planets, that glowing of the Mercury, right? But they're planets. And so far they have found what we expected, which is that planets B, C, and D do not have atmospheres. They're airless like Mercury, which is not surprising because they're not in the habitable zone. They're orbiting even interior to what would be Mercury in our own solar system. All right, so keep your eyes open for this kind of work, because as the years progress, we will get more and more data of the more distant planets and maybe start to understand if these planets orbiting red dwarfs are able to retain atmospheres. Okay, I do want to leave some time for questions, so I think I'm going to actually stop there. And I'll just end with this slide. This is a quote from a report that was written around 2015. NASA asked a group of scientists to come together and to lay out a roadmap for the next 30 years based on the Kepler discoveries. I participated in that effort, and so we laid out a technology plan for how to turn this into the search for life. And there's this sentence in there that is just, I still stand by today, and everything has played out so that what was going to happen in 30 years is now going to happen in 20 years, and we're still on track for that. And so the quote is there life on other worlds? For the first time in human history, we have finally been able to embark on the systematic, scientific pursuit of an answer. So it's something to look forward to. So don't be dead. Stay alive. All right, thank you.
Okay, so we do have time for a few questions. Go ahead. Yeah.
Yeah, you showed a slide in the beginning of all the exoplanets that have been discovered.
Yes.
My eyes are not good, but I think on the left side there was the size of the planet.
Yes.
Okay, so 2 questions. How can you tell, maybe compared to the sun that they're next to, how can you tell the size of the planet? And then second is, what is the methodology so that you're not double
So they're not double counted?
All those dots represented exo. How do you know when you look that somebody else didn't something that already did?
So, boy, I wish I had the right, I should have put backup slides to show this. So the Kepler spacecraft looked at a patch of sky about the size of my open hand in the constellation of Cygnus, more or less close to the plane of the Milky Way galaxy. And it had a mosaic of something like 20 detectors, and they all take images. So we see the salt and pepper of all the stars on the focal plane, and we define stars, and we cut out these little postage stamps around the stars. We cut out those digital numbers that are read out onto our computers, and we turn those into brightnesses. So each one is unique. Now, in the observations of one star, you can have a dimming of light, and you can have a second dimming of light, right? Because there are multiple planets. Like in TRAPPIST-1, you have 7 planets transiting, so they're all producing diminutions of light. And so you look for the strict periodicity, right? Sometimes they even have the same depth because they're the same size, but they have different durations. If you have an Earth-sized planet that's orbiting really far away, it takes, the planet is going slower, so it takes longer to transit its star. So you can see these subtle shape and timing differences to disentangle different planets in the system. Yep. Yes?
Not unlike Superman, I guess, where you want to be around a yellow sun. Do we think it's better to be around a yellow sun than a red sun?
I hope not, because 70% of the stars in our galaxy are the red suns. Only 20% are stars like our sun. Now, things happen when you're orbiting really close to your star. You experience more tides, and that can cause tidal locking, so that the planet is always, as it orbits, it's always facing the star in the same way. So you're always going to have a day side and a night side. But if you have an atmosphere, you can redistribute heat so that you can create more niches for habitability. The other good thing about the sun, they're M dwarfs, that's what they're called, these red dwarfs, these red stars. The other good thing about them is that they will live for trillions of years, whereas the sun only lives for about 10 billion. So you have orders of magnitude more time to evolve life. That's very exciting, and you have more of them. So my take on the M dwarfs is that it might be more difficult for life to get a toehold. There are other reasons for that as well, like magnetic activity of the host star. But you have more time to evolve, so maybe you'll extinct, restart, and you'll build up something that's robust over time. So I find that very exciting. Yes, you and then you. Yes.
With James Webb, about how many spectra of Earth-like planets would you expect to be able to get, let's say, probably in the next 5 years?
Well, the director of Space Telescope just allocated 500 hours in the next cycle just to observe Earth-sized planets. And for the Earth-sized planets, again, we're going to be answering this question, do they have atmospheres or not? If we want to go beyond that and actually find molecular, lines and absorption from molecules and know what greenhouse gases there are and all of that, you would have to devote a lot of observing time. I'm not that enthusiastic about that approach because there are so many open questions that we have that we can answer in at a much faster cadence. So I would like to see us understand the diversity of planets, even the larger ones. I would like for us to understand what life is not, so that when we build the next flagship mission, we'll be able to recognize life when we see it. That will be capable of detecting the habitable planets that are Earth-size. That wasn't what James Webb Space Telescope was built for. I want to know what these weird super-Earth sub-Neptunes or mini-Neptunes are, for example. Yeah, but we'll see some. Let's see, it was over here next.
You mentioned that with the transit method, you can measure the orbital period of planets, and from that you can find the radius and whether it's in the habitable zone. How do you do that? Can you measure the mass of the stars accurately enough to do that with Kepler's law? Is there some other way to do that? Like, how do you use period to find radius? Do you know the mass of the star?
So when you observe an eclipse, how much dimming of light you get tells you the radius. That's all you need. And then the time interval for them to happen in succession, that's the orbital period. So we get those two quantities directly without the need for any other observations. But now there are other techniques indirect techniques for detecting planets, like the Doppler method, which Lick Observatory is famous for. And that gives us mass. So if I have the mass and the radius, that's great, because now I can calculate the average density, and that tells me something about composition. And we've done that for about 1,000 planets so far, 700-ish. Yeah.
One more question, I think, but then you can always come and talk to us afterwards.
You said earlier that there was a possibility that there are planets orbiting two stars at once. What would the orbit of that look like?
I'm sorry, I lost what you said. I said earlier what?
You said earlier that there is a possibility that there are planets orbiting two stars at once. What would the orbit of those planets?
So in these cases where you have a planet orbiting two stars, the planet tends to be a lot further away. The two stars are in a very tight orbit. There's one that was nicknamed Tatooine because of Star Wars. Somebody from Lucas discovered. Those two stars are in a very tight orbit, and the planet is much further out. So actually, as far as the planet is concerned, it's like orbiting one star. But there are other cases where you have two stars widely separated, and then you have a planet orbiting one of them. But then that system is gravitationally bound.
That's how you avoid the three-body problem?
Centauri Alpha. You can have situations where a planet would be dynamically unstable.
Thanking our speaker again.
Thank you.